So Bobby, are
You are
those?
thinking about new applications.
No, I mean I'm just wondering are those all the applications for
Hmm.
strain gauge? Now we've seen quite a few applications.
Yeah.
I'm just thinking if there are, I mean, there are, very versatile kind of sensors. So I'm thinking, can we use them for some other applications? Can't really think of on the top of my head, but
I have some figure here. Maybe that gives some idea what we are planning to discuss. Let us say. So I have a disk kind of thing, and there is a hub here. That's a shaft there,
yes,
and there is some distance and force, etc. So
so it's post distance. So talk about torque now.
yes. So torque. So how do you measure torque?
Strain gauges.
So maybe the question is why do you want to measure also? Because see, let's say somebody designed a motor, says okay, it can take this much load. How do you know? So there should be a way to test it.
Yes.
Or some cases maybe you wanted to ensure that your drive or your motor, it could be any kind of rotary mechanism that's not overloaded.
Yes. Because your RPM doesn't necessarily have to
Yeah.
for your torque. Yeah. Then they're
Correct.
two different things.
Correct. One thing it is rotating, other one how much load it can take. Exactly. So basically there is a drive and then there is a consumer.
Okay.
I mean, I'm driving this, whatever load it is.
Consumer is the load.
Consumer is a load here. So it is transferred through this shaft. Usually mechanical coupling between these two. There will be some arrangement here to, there is a shunted mechanical coupling available. So the question is, how do you measure this torque? So as you said, this is a force into distance. That much we know. But measuring this, one way, something I have seen is people, let's say for this, let's say if I have a disk here,
Okay.
maybe I'll draw it here. And if you can have a, let's say, a belt. Of course, the belt will not be like this. It will touch and go. This is not correct. Yeah. So then, suppose if I can measure this force seen by the belt. I mean, suppose if I am rotating this, then what will happen? This portion will get pulled and this portion will get released, correct? Pushed. So I can measure these two and then find out how much is the load it can drive.
So you have something like a dial or something.
Correct. That's one way.
Yeah.
But this can be maybe one time. I mean, this is not something I can introduce to a system which is always running.
Yes. And you might have to, replace the belt. And
Yes. There will be a lot of frictional losses also here. Not a great test, but it could be one way to do this. This we do in a laboratory. But in practice, let's say in an industrial load, if you want to do this, how do you do? That's the question. Now, I have some figure to illustrate. So let's say you have a tube, metallic tube. Okay. And let's say that's the one which is used to connect these two.
Okay. Right. The drive and the consumer.
The drive on the consumer. And one side of it, I am trying to rotate. The other side, consumer is, putting some load to opposite. So there is a amount of twist housing. Yes, correct. So if you, let's say, put a mesh like this, like I have drawn here. Let's say if I have a proper drawing like this, and if I twist the structure. See, initially, the mesh that I've drawn will be like this.
It's just kind of a square
Square shape.
shape.
But after the twist, what I will see is this has got increased and there is a compression in this direction.
So that basically a square has somehow deformed.
It just deformed, exactly. So there is an expansion in this direction and there is a contraction in this direction, 45 degree. Yes. Correct? Yes.
If you
So-
twist it.
Yes. Maybe not great example, but if you, I don't know, after the bath, if you usually squeeze the bath towel. Correct?
I don't know, but new Bobby.
Some people do.
Yeah, I know what you're talking about.
Yeah.
Yeah. Yeah.
So when you squeeze that, you see the angle of,
Yes. Also, that's I mean, I didn't know it was 45, but I see what you're.
yeah, so it will be at 45 degree afterwards. Or even your skin, if you do a twist like this, there will be a 45 degree angle.
Does that depend on the amount of twist, or but you're talking about in general?
Yeah, the major component will be at
45
angle. Okay. So that means now we understood
Yes.
there is an expansion and contraction.
I see where you're going now.
Yeah. So I'm going to place strain gauges at that angle. Let's say 45 degree. And then sense this. Maybe I'll put one more I need not measure at same point.
Uh-huh.
This is uniform across. So I may place something which is sensitive to the, expansion and another one which is sensitive to the contraction.
But this is the initial placement of these.
Yeah.
Yeah, this is not
Where do you place? Since we said strain gauge, now the question is where will you place
where and how.
at what angle you will place?
And so angle, how do you calculate the angle? You take a straight line.
Yeah, with respect to the horizontal. So I have a better figure. So if you look at here, so this is before the twist, etc. Of course, this twist is not as big as the bathtub is mentioned.
Because you want to get to the water, so we go.
Yes. I mean, just for us
The visual, let's say.
everybody get use that. And here it will be micrometer level expansion and contraction, of course. Yeah. So this is a horizontal direction. I have kept this strain gauge at 45 degree. And this is sensitive to this direction. Yes. And you see other two, part of the other two, because it's a circular shape. The rest of it is not visible from this side. Yes. So, or if I take a cross section, basically we have 4 strain gauges kept like this.
In like this.
Yes. So there is, this one is this one, and this is in the other side of it, and these two are here.
Okay, yes.
Suppose if I make a cross section and then look, they will be present something like this. Right? So what I have drawn is the same mechanical rigid component which is present there. That alone is drawn here. Yes. So as I mentioned, they are in the 45 degree.
But placed in a way that the effect on them will be opposite for the ones that are facing each other.
Yes. Right. Yeah. So this is under expansion. And the one in the opposite is also an expansion. Same thing here. Contraction and contraction. Yes. So now as you can see, we will be able to form a full bridge. Because you have 2 sets of resistors, they are changing in a push-pull manner. Yes. So we have the full bridge. But there is another challenge which is hiding there. As you can see here, I have a motor which is driving this load. Yes. Of course, driving, it's rotating. Yes. Now, to measure from this strain gauges, I cannot have 2 wires. Correct?
Yeah, it will get all tangled up.
So,
Right? It will also get tangled up.
yes, that will be very
It will be a disaster.
correct. Yeah. So, that's not a solution. So, I need to somehow make measurements even when the rotor is rotated.
So, but you have to make measurements on it.
Correct. How do you do?
probably need.
Yeah, we need some electrical contact to make this measurement.
Yes.
At the same time, it should enable the rotation. It should not stop the rotation. Yes. Right. So there is, you may know something called this ring that slips. Slip rings.
I've heard of slip ring.
Yes. So that could be used maybe.
Ah.
So in a bridge, of course, we have 4 points to connect. My bridge drawing is getting poorer and poorer and poorer. But anyway, so as you can see, I need to make connection with, let's say, A, B, C, D. Yes. I mean, one thing is to power, either AC or DC. And then the other two is to measure. Maybe a meter.
So the strain gauges, what about the strain gauges? They I guess they have to be placed on the cylinder.
Correct.
They have
Correct.
to. That
Yeah.
is-
So
that is non-negotiable.
yes,
right?
yes, that is not negotiable because that's the strain that you want to sense.
Exactly.
So the strain seen by the mechanical coupler or the rod, we'll call it as a mechanical rod. The strain seen on that surface is that we are measuring. Yes. So the strain gauge has to be fitted firmly on that. Yes. Only then it.
When really experience the
Yes. Yeah. Only then it will.
deformation.
Correct. Will be transferred to the strain gauge.
So the output of that somehow has to be kind of
Yeah. So now the bridge has to be excited.
yes.
And the bridge output has to be measured.
Yes.
So 4 terminals.
Yes. So the once you place the strain gauge, you have the terminals there.
Yes, of course.
Yes. But then, how do you actually make that connection?
That's the thing. So as you can see here, I have introduced 4 rings now.
Okay.
A, B, C, D.
Okay.
So these are rings like this. Underneath you have the rod that is rotating.
Okay.
There will be insulation between these two. And this red one is the ring which is conductive.
Okay.
So if I can have a brush here, I mean in the sense, let's say you have a contact like this, maybe a carbon brush and a copper ring.
You can't touch.
So they are always, there will also be a spring to push this always so that they are always in touch. And then this contact is maintained.
But then, are you not affecting the rotation or the speed of the motor?
So the assumption is that the friction introduced by these contact is negligible compared to the load that you are.
Aha. Okay. I see. Fair enough.
Yeah. Otherwise, as we said in the beginning of the course, by putting this, if it slows down,
Yeah.
then
Right, then there's no point, right?
Yeah.
There's no point in using a sensor.
correct. Then you are loading the measurement.
Right.
That's against our policy. Right. Yeah. So I have this electrical contact, and let's say this is A. Like this, I will need 3 more to form this 4 connections to a full pitch.
Right. And this is inside something.
Yeah. So as you can see here, so the strain gauges are here. They are connected to the bridges. Sorry, the slip plates like this.
And you take the output.
Then, from these brushes,
Because they are not moving. So,
correct. From this brush, I can easily take the electrical motion. Only thing is, this contact point is key. If that contact is lost, you cannot measure.
correct.
Yeah. So I have a better drawing of this. I think, yeah. Maybe it is, yeah. So as you can see, there is a bridge here.
Mm.
So the points, let's say A, B, the excitation voltage is given here. That I can give the outside. Yes. So this is only the electrical diagram. Right. The physically A, B, C, Ds are present here. So those ABCDs are shown here. Let's say A, B, C, D, the rings. Yes. To the ring, we have this brush, which is touching. In this drawing, it is seen as not touching, but it's touching like I've drawn earlier. So I use A and B to give the excitation voltage. And as you can see, these two are used to bring out the output voltage. Yes. I think it's straightforward. Yes. I think so. I get the output here, I get the excitation. So this part is, as you can see, it's rotary, it is rotating, while the brushes and other things are stationary. Right? Now, as you said, one problem is this contact. If the contact is lost, you cannot do anything. It may also load. There will be frequent maintenance probably to replace the brush and so on. Also, there will be little bit of loading due to this. So it's not something that we prefer, but this is one way to do it. Right? You may prefer if this measurement can be done without having this slip ring arrangement.
Some contactless.
Correct. Because this is always, what shall we say, reliability concern. Yes. I'm not sure whether doing the really in contact or not. We don't know.
Yes. So, I mean, that might affect the output. I'm not sure.
Correct.
So she said, maybe you need regular maintenance. And if you have hundreds of these machines, then maybe it's not optimal in an industry setting.
Yeah. So maintenance will be an issue. Reliability is a concern. So this is not the best solution, but this is one of the possible solutions. So what else can be done?
I'm not thinking, is there any way that you can do contactless?
Yeah.
No.
But somehow the measurement has to be made from this.
Maybe it's true. Strain gauges here are not the problem.
Correct.
And we can't do much with the actual rod because it's there.
Correct.
Right?
Yeah.
What can we do to make this better? I don't even know if there's a way to make that.
Yeah. Somehow we have to wirelessly measure this change. Yes.
But the problem is you also need to give power.
Correct. We need to give power.
I mean, if you have power, okay, maybe you can think of some plain antenna or something to send the data out. But how are you going to give power?
Correct. So maybe we will think about it and come back.
Let's think about it.
Yes.
But I think I have a small idea. But let me think about it more.
Yeah.
And then come back.
Yeah. So we are stuck with the slip ring. Yes. And
brushes.
Yes.
How about something? Can you power the sensors wirelessly?
Wirelessly? Yeah, wirelessly. But how? In a non-contact way, how do I transfer power? Electric power.
Non-contact way transfer. Something like a transformer.
Sorry. Yeah, we could do that.
Can we?
I think so. And suppose if I have a...
How would you design something like that?
That I don't know. We'll see. So suppose if we have a transformer coupling, transformer. Let's say I have a primary here. That is excited. Losing some sinusoidal wave.
Okay. Yeah.
I make a secondary. These are magnetically coupled. I will connect that to this terminals here.
So still there's a connection.
There's a connection, but the secondary can be on the road.
That's perfect to coil around, right?
Yeah, exactly. You can wind it on that. Primary can be on the stator part.
Yes. Okay. Right. So then you have some...
Yeah, so we have excited the bridge now without any physical connection. Yes. So it's free to rotate. Now I need to take measurement from the bridge. I mean, bridge is excited. There is a change in output. Earlier we marked here. Now just for convenience, I marked the outside. So I have C and D here. I need to measure this and bring this out to the stator. Yes. Yes. So definitely we will need one more coupling like this. Yes. Another coil. Another set of coil. So let's introduce one more set. So the bridge output is connected to one of the coils. That is on the rotor now.
That's your primary then.
Yeah, kind of. Correct. Yeah. And then I will have a secondary receiver, which is on the stator. And these are magnetically coupled. And then I measure this. What it? Yes. This will work. So this is a possibility. Yes, this is a possibility. Oh, sure. So only some issues may be, let's say if this gap changes for some reason.
Then your voltage might reduce.
Yes. Then this, let's say this M2, the coupling between this and this. Yes. If that changes, then my output will change. Similarly here, the excitation that I am giving, this coupling M1, if that changes, there will be some error in the output. Of course, we'll have to give AC excitation. If I give a DC excitation,
there will be nothing.
There is no voltage induced in the secondary and the bridge is not excited. And
Yes.
So,
But, I mean, the space between them should not technically change, no? Unless, your rod kind of starts moving up and down.
yeah, I mean, let's say we fix today, after 10 years, there may be some mechanically misalignment, right? So, earlier my coils may be perfectly aligned, although not in my drawing, but let's say they are like this. But after some
10 years, it's like that.
10 years is like this. Then the coupling will change. Right.
But then if you do regular maintenance,
Yeah, but we don't want that.
we don't.
But of course, this is better than I have a better drawing here. Slip rings. Because there is no mechanical contact required to the rotary part. Yes. Right. So you have the primary coil here. Although it is drawn like this, it is wound on top of this. I mean, you have the secondary and primary on top of one on top of the other with an air gap. Then the voltage is induced in this one. That is given to the bridge. Bridge output is connected to this winding, and that induces a voltage here, which is being measured. Yes. This is one option, but as I said, it's again a little bit sensitive to this coupling, the magnetic coupling between the stator and rotor coils. Okay. So, is there a way to improvise this?
You mean?
I mean, this M1 and M2, they tend to change over time.
I guess so.
We will not have 100% control over it. Yes.
And also, I guess if you have a change in the voltage because of that, you might not know if that is due to
close or due to something else. Right? Yeah.
So that, yes, you're right. That could be a problem.
Correct. So one way could be we can modify this. I mean, now instead of directly giving, what we will do is maybe I will introduce a rectifier unit here. Let's say another block with diodes and so on. Somehow I will rectify this. And then maybe I will have some regulator also. Let's say I use a regulator circuit to get a proper DC voltage. Okay. that I will give to this.
So now you're getting a DC voltage.
So that way, here it is AC which is given, but then this block gives a proper stabilized DC excitation. Okay.
To the bridge.
To the bridge. Okay. So that way, even if M1 changes to some extent, let's say 10% variation, I will still have, constant output or constant voltage at the bridge Vs.
Okay.
So that problem is solved. Now the bridge output will be DC, correct? Because bridge is excited using DC. So this will be a problem.
But the DC voltage can also change with the.
That's where I used it's not just a rectifier. See, suppose if I have only rectifier.
Oh, yeah, regulator.
Yes. Okay. Yeah. So I get rectified this, and then I use a regulator IC, a voltage regulator IC, to get a proper DC voltage. Step back. Yeah. Of course, there is some range of variation,
right,
that is permitted for the hours.
But you have some tolerance.
Yes. So, of course, rectifier full wave bridge, they have studied, explain that. Okay. All right. So, I would maybe write a regulator. DC voltage. Okay. But now bridge output is also DC.
Yes.
This means this coupling will not question.
Yeah. So then you have to somehow change it back.
Yes, somehow I'll have to introduce something here.
Change it back.
To convert this DC voltage to an AC voltage. So I will introduce what shall we do? Maybe a voltage to frequency converter. It's an operation with the basic circuit. Let's not go into the details. Yeah, let's say this is given. Now I have a frequency output. Yes, if I have, let's say, 100 millivolt output for the bridge, maybe I'll get 10 kilohertz. 100.1, I'll get maybe 11 kilohertz and so on. Yes. So I'm converting this voltage to a corresponding frequency. And then we can easily give this to a coil. So here we will not measure the voltage. Instead, we will look what's the frequency of the signal. We'll have a frequency measurement.
But doesn't matter because that can be correlated to the.
Exactly. So now M can change. So the amplitude of the signal induced here will change, but of course not the frequency.
Yes.
Frequency will reverse. Yes. So that way, almost all the problems are solved.
You totally get rid of the block. This
spacing. Correct. Yes. So variations in the magnetic coupling is removed now. That issue is removed now. Of course, we are hard to introduce a little bit of electronics here and here.
But those electronics you can easily introduce in the stator.
Yes.
So again, that's not a problem.
Yeah.
So this is definitely, I think, a better way.
Yeah. This is a very, very nice way of reliability is high now. There is no friction, no contact issues.
Yes.
Perfect.
And you're not modifying the actual setup.
Correct.
Right? Your drive, your consumer, your rod stay the same.
Yes.
Right? So you're just winding a coil around.
Yeah.
Again, that will not affect the speed or the torque, right? Because the brushes, I asked you a question and you said maybe, but
correct,
depending on the load, right? But in this case, you're just winding a coil. That's it.
Yes.
And the stator can have all the other electronics.
Yes.
So a nice way.
Exactly. We just need two sets of concentric coils.
Yes.
One on top of the other.
Yes.
So I have a better drawing of that here. It's the same circuit. You have the excitation given to the coil. it is rectified and stabilized, given to the bridge. Bridge output is converged into a frequency output that is coupled to this, and then it is measured. If you need a preamplifier, you can use that before giving to the frequency measurement.
But again, we can work with frequency, right?
Yes.
So amplitude is not that incorporated.
Yes. If I want to measure speed, I mean, this drawing also has a RPM measurement unit, but it's independent of that. Okay. If you want to measure the speed, then this is an optical mechanism which is used, which we will discuss later.
Right. So here, the output, I mean, we don't really want to measure the amplitude though, right? Because then you're introducing the spacing again.
Correct.
So, I mean, even if you get a small amplitude, you can have a preamplifier. But then that probably doesn't make much sense, because that if that amplitude itself is changing because of the spacing,
Yes.
then it's not very reliable.
Yeah.
Right?
Yeah. That is the reason we have converted this into frequency, and then that signal is passed.
Signal is passed.
So it's no more relying on the amplitude. Amplitude has to be just sufficient enough so that the measurement is possible.
Right.
That's right. So since this is a same drawing of what we discussed in the previous one, we are not going into details. It's the same.
Again, using strain gauges.
Yes. Now, only thing is it has become a little bit bulky. You have two coils.
I guess so, yes.
Yeah. So that is there. Yes. Now, in case you don't want that also, in some application, maybe I don't need to measure for low time.
Okay.
So just for a study, I maybe introduce a torque sensor, record everything. Okay, this is good. This is meeting the requirement. Probably that is what we are looking for.
So you're saying, so you're not talking about this specific application. So you're saying this is the best way to measure for this driver consumer rod application. This is the best way.
Yeah. But if you want to measure continuously in a system, this is good. But let's say I want to just monitor once, and then I'm fine with that. I'm not going to record for years. I may record for a couple of days. Then, you had actually suggested something before, using antenna also. What is that?
Oh, antenna, yes. I said,
Since you said wireless.
Yes.
I
said, why can't you just connect some sort of antenna?
Yeah, so for example, what you are saying is, this one, instead of a magnetic coupling, if I have an antenna here, and if I transmit like a radio, that should also work.
Correct.
Only thing is, I need power.
Yes. So my problem was power, right?
Power. Correct. Right. So power, I mean, one way to give like this, but if it is for a short measurement, I can have a button battery there and connect.
This is true, yes.
Right? Because here, what we have introduced is you have a regulated DC power supply. It can be a small battery. So if your application is not for long term and so on, I can have something like that.
So even for the consumer driver rod setup, we can still use a battery. Is that what you're saying?
Possible. Only thing is,
you need to replace the battery.
Yeah, we need to replace the battery. Right. So that kind of approach is also possible. For example, like this.
Okay. I see an antenna now.
Yes. So we will not use this winding based transformer coupled approach. Instead, I mean, for example, here a strain gauge or a torque sensor is introduced here, but it's just powered from the button battery. And then you have a transmitter here and a receiver here.
And they response to the data.
That's it.
Yeah. I mean, that makes sense. Because you said if you don't want to measure something regularly, for period of time, if you're sending, once every week or once every day, once a day.
Correct.
Then you can easily use a battery and the battery will last for a long time.
Correct. Yes. So this is, for example, it could be to measure, some new design is given to the rim, right? And somebody wanted to see how it performs.
Yeah.
So could be for torque or some kind of deformation and so on. We could use some.
Right. Right. That's, yeah. Right.
So this is also a possibility.
I think for an industrial setting, I still like the coil-based
Yeah.
version.
Yes.
I think it's, you can easily, it's very scalable for large number of machines.
Correct.
And you don't have to replace batteries.
So yeah, because always a popular, yes. Yeah, because otherwise there should be somebody to look for whether the battery is now or not, just replace that.
It's not going to practical, right?
Correct. So there, this solution is perfect.
Perfect. Yes. Correct. But again, you've given several options, right?
So it's up to the designer.
It's up to the designer.
Select
The use case, the industry,
Yeah.
type of machine.
Correct.
Yeah. So strain gauges, yeah, I'm very impressed with strain gauges.
a lot of very nice applications.
Yes. I think you've shown that, strain gauges themselves, fine, they do a certain job, right? We know what they measure. But then there are so many other ways, obviously structural, structure-wise or from electronics point of view,
Correct.
where you can actually combine,
Correct.
all these different ways of measuring something using strain gauges. So I think it's a very, very nice setup.
Yes.